discrete time signal defined for some specific instants of time. Okay, and these instants are of course 0, ts, 2ts, 3ts, 4ts, minus ts, minus 2ts, minus 3ts, and so on. So okay, for some defined for some specific instants of time, understood? And guys, if we talk about this signal f of n, so this is of course a discrete time signal. But you can realize one very interesting thing about this signal, because here I have taken ts equal to 1. Now listen very carefully. Here I have taken ts is equal to 1, n is integer. So can I say this discrete time signal define only for integers? If someone says to you discrete time signal defined for integers, that means he is talking about f of n. Okay, he or she is talking about f of n. Okay, if someone says to you discrete time signal defined for some specific instants of time, not defined for remaining instant of time, that means they are talking about a general form of the discrete time signal. Okay, so understood, discrete time signal is, actual definition says it defined for some specific instants of time, not defined for some instants of time. Okay, discrete time signal, which is we have represented as f of n, is actually mean that it defined only for integers. So throughout this subject, except the sampling criteria chapter, we will use ts is equal to 1, because ultimately ts is equal to 1 will make the discrete time signal representation very easy for us. F of n, that can be easily represented for various values of n, means you can represent like f0, f1, f2, f3, in negative side as well, -1, -2, and so on. Okay, all these values we say are the defined values. But here if I say f of 1 by 2, f of 3 by 2, you will say not defined. Okay, these values will not be defined here, because we are defining f of n where n is integer number. Okay, so f of 1 by 2, f of 3 by 2, all these things are defining the non-integer parts, so of course it is not defined here. Understood? So please note this discussion down. So from now onwards, we will talk about the discrete time signal which is defined only for the integer. The purpose I already told you, we are considering here the special case of discrete time signal where ts is equal to 1 is taken. So let's write here one point. F of t is continuous time signal that is defined for any real value of t, whereas f of n is a discrete time signal which is defined only for integer values of n. Means if I want to represent, suppose I represented a signal f of n, let's take an example here. Means suppose I said that like f of n a signal that is having the value, suppose -2, -1, 3, 1, comma -2. Okay, and here I indicates that index. So guys, this index always says, now listen very carefully. Okay, here we are going to just introduce all the philosophies related to the discrete time signal, those we are going to utilize in this subject throughout. So please listen everything in very conscious way from now onwards. Okay, see, this is n is equal to 0 line. Okay, if I move into that side, means from n is equal to 0, that index will always define n is equal to 0. In upcoming time, I'll not even write n is equal to 0 here. I'll simply mark here index. That index, this arrow basically, index means that index will definitely define n is equal to 0 line. And you know that this fn is a discrete time signal that defined only for the integers. Means in the right side, the values of n for this 1, here it is 2, and so on. And here it is -1. That -2 value is what for? N is equal to -2. N is equal to 0, n equal to 1, n equal to 2, n equal to -1, n equal to -2. Means if I represent this signal f of n over here on the n scale, see how can I represent it? See here, for n is equal to 0, the sample value is 3. Sample value is 3. For n is equal to 1, sample value is 1. Sample value is 1. This is the graphical way of representing it. N is equal to 1. Okay. For n is equal to 2, sample value is -2. This is for n is equal to 2, this sample value is what? -2. And for n is equal to 3, here we have just mentioned the non-zero samples. Particularly, we mentioned the samples, those are having significance. Now you can say for n is equal to 3, definitely you will say the sample value is 0. For n is equal to 4, definitely you will say sample value is 0, n equal to 5, 6, 7, 8, 9. You may take any n value here. For all those sample values are to be 0, of course. And if we say in this side, n is equal to -1, sample value is -1. Here it is n equal to -1. So for this, sample value is what? Again, -1. And guys, if I say for n is equal to -2, the sample value is -2. Like this. So this is how we represent. And for n is equal to -3, it is what? 0. So this is the way of representation of discrete time signal. Understood? So any of the discrete time signal is represented in front of you, that is written as f of n. You must have to keep this thing in mind, that is only defined for the integers, not defined for the non-integers. So let's write here one point. The discrete time signal fn is defined only for integer, and it is not defined for non-integer. Okay, here n that we have taken is only the integer value. Understood? Now please note this discussion. Noted. So guys, we have seen some important time scaling operations over the continuous time signal, over the continuous time scale. That was, we have seen the time scaling, time shifting, time reversal operation. Now let me tell you how these operations will be applicable over the discrete time scale. Obviously, the philosophy of applying these operations, whether it is time shifting operation or it's time scaling operation or it is time reversal operation, is same for continuous time. Similar approach will be utilized for the discrete time scale also. So don't be worried about, don't be scared about it. Okay, philosophy is same, conceptual discussion will be same. Few things are there, those you have to be keep in mind. So let's apply the time shifting, time scaling, time reversal operation on the discrete time signal. So let's make a subheading over here. Operations on basic operations, basically operations on discrete time signal. Discrete time signal. Let us talk about operations on discrete time signal. See, first of all, let's write first one. If I'm writing time shifting operation, Guys, I'm just hoping that you all have revised the time shifting, time scaling, time reversal for the continuous time scale. I'm just hoping that if you have all revised that section, then it will be very easy for me to explain it, and it will be easy for you to grasp it. Okay, so please, if you have not revised that continuous scale, time shifting, time reversal, time scaling operation, then you should go for that section first. Okay, then attend this class. Okay, now I'm just expecting that you have revised it. Now let's come to the discussion. Time shifting. Again, I'm taking, guys, the same function f of n that I have just taken before. Suppose I'm taking this f up to n is equal to -2, -1, comma 3, comma -1, 2. Or what I said, I think we have taken 1, comma -2. It's fine to take any other. Okay, here it is n is equal to 0. And by default, this side if we move n equal to 1, 2. Okay, I'm just writing it for the initial steps. Later on, I will not write it. Okay, you must have to keep this thing in mind. Only index will be represented. That defines n is equal to 0 position. Now, if I'm saying to you, let's write f of n minus 3 for this. See how it will be represented. F of n minus 3. Guys, have you remind in continuous scale what we do? When we write expression n minus t minus t naught, in graph what we do? Add t naught at each and every instant of time. Here also we do the same thing. What you will write? Add 3 in each instant of time in the graph. Okay, what we will do, guys? We will simply add 3 at each and every instant of time in the graph. Let me represent it. So guys, this f of n will be transformed into f of n minus 3. So here, if I represent the graph of f of n, okay, this is suppose a scale, and on that scale, I'm just writing it little bit rough diagram, okay, for your understanding purpose basically. This is n equal to 3, n equal to 0, where sample value is 3, n equal to 1, sample value is 1. For n equal to 2, sample value is 2. For n is equal to 3, sample value is 0. Similarly, for n equal to -1, sample value is -1. Please pardon me if you are not feeling the samples are of equal size of the same value, okay? We are not here to design, to do the drawing part here, okay? I'm here to give you the conceptual understanding. And you also know that thing. Please excuse me, I'm not that much good in the drawing of the diagrams and figures, okay? So let us draw the f of n minus 3. What I mention here as a statement, what I mention here, guys, as I mentioned here, just perform the addition of, what you will do, guys, just perform the addition of 3 at each and every instant of time. The same thing we have also done in the continuous scale. So here, see this, don't add these 3 in the sample values. Don't make the mistake. We are not performing here operation on the value scale. We are performing here operation on the time scale. So please keep this thing in mind, because in discrete sense, time scale and value scale looks identical. Okay, here I'm saying 0, 1, 2. You are also seeing here 3, 1, -2. So this is a very common confusion. It's not a confusion. It's a silly mistake that can happen. Sometimes we start adding the numbers into the values. Values will not get changed. Please keep in mind. Sample values will not be changed. Just we are shifting these sample values. We are making n minus 3 means we are making it delay by the 3. So of course every instance here -2 will be added with +3. What will happen, guys? Tell me. If I add here 3 plus 3 at this location, plus 3 at this location, plus 3 at that location. Please keep in mind we are adding everything in the location, okay? Plus 3 at this location, plus 3 at this, plus 3 at that. Okay, just I'm writing it roughly, I'll erase it. Okay, so minus 2, what the sample present at t equal to n equal to minus 2, that reaches at plus 1, means this time that sample will be reaches here with value minus 2, of course, at 1. 3 plus 3 minus 1, what will be here? It will be reaches at 2 with sample value, of course, minus 1. This sample which is present at n is equal to 0 will reaches at this time n is equal to 3 with sample value 3, of course. Okay, and here you can say this sample which is present at 1 will reaches at 4 with sample value 1. And guys, you can say this is present at sample value 2 will reaches at 5 with sample value 2. Okay, and all other are to be 0, of course, so we don't have the need to write. So this is f of n minus 3 we have written. Now let me write it. So here n is equal to 0 sample is present, so I must write it as here 0, because it is important to mark the index line, means n equal to 0 you have to be right here, otherwise you will not be able to identify which is n equal to 1 2 3 4 5 and which is minus 1 minus 2 minus 3. Okay, so here I have represented 0 by the index here, and at n equal to 1 what is sample? Minus 2, here minus 1 3 1 minus 2. This is f of n minus 3. What you have seen, that one and that one, what is difference in both of them? Just we have put it here and shifted into the right side. Every point of time we have added added the value plus 3 at every instant of time. You must have to keep this thing in mind. We are performing here addition at the instants, not on the value axis. No values get changed. Minus 2, minus 1, 3, 1, minus 2. Minus 2, minus 1, 3, 1, minus 2. Sample values will not be get affected. We are performing operation on the time scale. Sometime this mistake happens in hurry. If we in so much hurry, then we make such kind of fool mistakes. Okay, so you have to keep this thing in mind. This is f of n minus 3. Everything is same. Here we have done the addition equivalently. So of course guys, you can say this is the delayed version of the original signal, delayed. I'll not write so much things in detail because we have already done the discussion over the continuous scale. I'm just giving you here the philosophy of discrete sense. Okay, so most of the things you are aware of, just we are correlating both of them. Let's write the advanced operation also here. Let me do f of n plus 2. Guys, let us represent f of n plus 2. Visibly here in the expression what you are seeing, addition of 2. What we will do guys, subtract 2 at each instant of time. What we will do guys, we will subtract by 2 at each instant of time. Let us find f of n plus 2. F of n plus 2. What we will do guys here, we'll simply subtract by 2 at each and every instant of time. Every instant of time. Okay, so this is f of n we are having. So let's perform the subtraction by 2 at every location. See, minus 2 is here. The extreme left section is sample is minus 2. Take minus 2 here, subtraction. What you will do? We'll reach at minus 4. Am I right or not? Yes. This will be reaches at minus 4. Understood? With sample value of course minus 2, but this time it will be reaches at minus 4. Minus 1, minus 2. So this sample will reaches at minus 1, minus 2. So guys, this sample will be reaches at minus 3. N is equal to 0 sample will reach at minus 2, which is having plus 3 value. Plus 3 value will reach as minus 2. And n is equal to 1 sample will reaches at minus 1. Somewhere here, and with sample value 1. At n is equal to 2 sample will reaches at 0 with sample value 2. Okay, and n is equal to 3, which is 0 sample, of course, will reaches at here 1. So you may clearly represent this f of n plus 2 will be written as, see, at -4 it is -2, comma -1, comma -2, comma -1. Did I make mistake? Yes. -2, -1, comma 3, comma 1, comma 2. That is that index. Am I right or not? Yes. So this is how we have represented the f of n plus 2. We have already done all these expressions, all these representation in the continuous scale, but here you can relate it very easily, so that I am writing every time it is okay. So please note this down. Noted? You guys, you have noticed one important thing over here. See, here we have required to add 1 0 because we have shifted it into the right side, so that to introduce the index sample we have added some 0 here. So this is called basically the procedure of basically we are adding here extra zeros into the sample. That is called zero padding or zero appending of the discrete time signal. Okay, maybe to perform the time shifting operation, it is required to add extra number of zeros in the right side of signal, or maybe in the left side of signal. That is called the zero padding or zero appending of discrete time signal. Let's write a note point here. Have you understood this all discussion that we have made over here? This is what we have drawn, guys. This is f of n plus 2. Please note the graph also. Note the every graph, all these 3 graphs you should note here, along with the expressions of every one. Okay, noted. Now let's write a note point here. During the processing of time shifting operation of discrete time signal, sometime it is required to add extra number of zeros in the right side or in the left side of the signal. This is called zero appending or zero padding of the discrete time signal. Understood? Now let us talk about the next operation, that is called time scaling operation, the second one. We have understood the time shifting operation on discrete scale. Now let us talk about time scaling. So guys, as usual, you know that time scaling means simply we are performing the compression or the expansion of the signal, as we have done its discussion in the continuous scale also. So time scaling is the something that is compression or the expansion of signal. Let us take the similar example once again. That was f of n, we are having -2, -1, 3, 1, comma 2. Okay, what I think I have taken -1 here. Okay, it's fine. This is f of n that I have taken, and we have also represented this f of n on the graph. Let me represent it very quickly for you. So at n equal to 0, its sample value is 3. At n equal to 1, its sample value is -1. At n equal to 2, its sample value is what? 2. This is n value, and at n equal to -1, its sample value is of course -1. At n equal to -2, its sample value is -2. Okay, this is f of n that we have. Now let us perform the time scaling. The first operation that I am doing here, suppose I am writing f of 2n. Guys, tell me what we should do here in the graph. Just recall what we have done in the continuous time scale. We have simply divided by 2 at each and every instant of time. What we have done, guys, we have divided by 2 at each and every instant of time. So what we will do in the graph, divide by 2 at each instant of time. Okay, means this is f of n, we are having, and we are writing f of 2n. So to represent this f of 2n, we should do only one thing. Every instance has to be divided by 2. Now look guys very carefully. See, here it is n equal to 0. Here it is 1, 2, minus 1, minus 2. Let me tell you one thing which is very important. This f of n, whether it is f of n or it is f of 2n, any of this discrete time signal which is represented in terms of n, of course, will not be defined for the non-integers. Understood? Guys, see, if I divide this 0 by 2, what will happen? No issue, it remains 0. Means here the sample which is present at n is equal to 0 will be remains as it is. Means this sample will be 3. See the sample which is present at n equal to 1, divide it by 2, 1 by 2. Understood? So at n equal to 1 by 2, there is nothing like n equal to 1 by 2 over this scale as well. This is the scale of n. So of course 1 by 2 is not existing here. When you will divide it by 2 here, that becomes 1. Means n equal to 1, the sample 2 will be present. We have lost this sample minus 1. Understand? Please try to understand that sample which is present at 1, once you have done its scaling by greater than 1 factor, this sample reaches at the non-integer position. Listen very carefully, it's a very important concept and very useful also for the further analysis purpose. Please listen carefully. What I'm saying to you, once we convert this scale of f of n into the 2 times scaled factor, that means we have just taken the greater than 1 scaling factor. So what we have realized here, the sample which is present as n equal to 1, which was present at n equal to 1, get non-integer position. And you know that non-integer position is not defined here. So of course you can say guys, here this minus 1 sample will be lost permanently. Okay, please keep in mind, don't get confused, we are not performing here the operation on the value scale, but we are performing over the time scale. But you should notice here time scale is not like the continuous scale where t value was any real value, but here n value is only integers. Means the sample which is present at non-integer will not be considered here. Okay, so here it is again divided by 2, so that sample will also lost, and here it will be minus 2 by 2, that becomes at minus 1 position. Means the signal which is f of 2n, we are not making any mistake, just try to understand, which is present at having only 3 sample, minus 2, 3, 2, and here I have represented index. Okay, just you have right index, that simply mean right side of it 1, 2, 3 possible values will be defined, and left side of it minus 1, minus 2, minus 3 will be defined. So this is the sample. This sample having 5 non-zero samples, but in the resulting one we are having only 3 non-zero samples. We have lost that one minus 1 and this minus 1. So while performing the time scaling, especially by taking greater than 1 scaling factor, you must have to keep this thing in mind, whether it is desirable or not, because it will lost the samples permanently. Means if you have done this f of 2n, there is no procedure by which you can regain this f of n, because here samples are already lost. There is no operation by which you can regain this f of n again, recreate this f of n. You cannot recreate here because you don't know which one samples was here, that we have already lost here. Okay, so this is called the decimation of discrete time signal. In the discrete time signal, while performing time shifting, we have discussed a very important definition, that was what? Zero padding or zero appending. Adding of extra zeros was called zero padding, zero appending. And here We are saying a word called decimation of discrete time signal. Let's write this point. Write a note here. Write a note here. First of all, note this discussion, note this graph, note this expression, write this also, and then write a note point. Have we done this? Now, let's write a note point. While performing time scaling operation, if scaling factor is greater than 1, in this condition, sometime number of samples in the time scaled signal is less than number of samples in the original signal. This is called decimation of discrete time signal. Okay, this is what? Decimation of discrete time signal. Now let us, please note this down. Note it. Now let us move to the f of second time scaling. Suppose I am doing n by 2. F of n by 2. Guys, in the graph what we have to do? As similar approach that we have also discussed in the continuous time. What we do exactly here? In the graph at each instant, at each instant, what you will do, guys? In the graph at each instant, what we will do? Here division is getting performed. What you will do? Here division is getting performed, so we will multiply it by 2, or we can also say divide by 1 by 2, because here scaling factor is f of n become f of an, and particularly here a is equal to 1 by 2. If you will be divide by a here, so you will say simply divide by 1 by 2. Divide by 1 by 2. Divide by 1 by 2, another way you can say multiplied by 2, or always. Okay, obviously it's the same thing to write. Okay, that's we have done in the continuous scale also. I'm just hoping that you all have revised that as well. Now let's reach to the f of n by 2. See, every instant will be divided by 2. Sorry, divided by 1 by 2 means you can say in other words, it is getting multiplied by 2. See, n is equal to 0 sample, will not get affected at all. Means you can simply write it over here. This is n is equal to 0 sample. If we talk about n is equal to 1 sample, that reaches at n equal to 2. Means this is a discrete scale where n equal to 1, 2, 3, 4, okay, 5, 6, 7 and so on. All these things are present like this. 4, 5, 6, 7. Okay, and similarly we also defines in this way. So here we can clearly define it like this. So obviously here you can say all the discrete samples -1, -2, all these locations are present here. Okay. So if we are dividing it here by 1 by 2, so obviously the sample which is present at n equal to 1 will reaches at n equal to 2. So obviously you can say here the sample is reaches at n equal to 2, which is having the value 1. Okay, sorry, -1, I'm sorry, -1, and the sample which is having the value 2, which is present at n equal to 2, will reach us at n equal to 4 this time. So what are the values present at 1? You should say 0 here. Okay, we can take here 0 or any well-defined sample. That is called interpolation of discrete time signal. By using the suitable interpolation technique, we can define the unknown samples present between the non-zero existing samples. Okay, if no specified sample is given, then we consider here zero interpolation. Means over these empty spaces we write the zeros. Okay, so this is for n equal to 4. Now let's talk about the sample which is present at n equal to -1 will reaches at -2. What was its value, guys? -1. So definitely it will reaches at -2. And sample which was present at -2 will reaches at -4. So of course here with sample value -2, and here it is empty space, so we will write 0. Means I must represent this f of n by 2 like this. Guys, see how it will be represented. -2, comma 0, comma -1, comma 0, and this is 3 where index is present. 0, comma -1, comma 0, comma 2. So you can clearly understand this is for n is equal to 0 point. Here 1, 2, 3, 4. Similarly, -1, -2, -3. These are the values of n. 0, 1, 2, 3, 4, -1, -2, -3, and -4. Understood? So this is the procedure where we have added the extra number of samples between the present samples. So in this one, we have seen the more number of samples as compared to the original signal. This is called the interpolation of discrete time signal. Let's write an important point. Write a note point here. Okay. So please note this discussion first of all. Then write a note here. Write another note. Right. During the time scaling operation, if scaling factor is less than 1, under this condition, number of samples in the resulting time scaled signal is greater than the number of samples present in the original signal. This is called interpolation of discrete time signal. What it is? It is called interpolation of discrete time signal. These unknown samples are defined by suitable interpolation technique, and if interpolation technique is not specified, then we use zero interpolation. Means we added extra number of zeros between the samples. So here we have done the interpolation by using the zero interpolation technique. Okay, interpolation, what we have done here, interpolation by zero interpolation. Okay, if either the suitable interpolation they will be specified you, means they will give you that unknown sample which comes in between these samples, that could be represented by k. Okay, k could be any value according to the interpolation that is provided to us. But if not interpolation is mentioned, that time we consider simply zero interpolation. Okay, so this is the time scaling operation. So in the time scaling operation, guys, what we have noticed time scaling can be done obviously by taking a scaling factor greater than 1, and obviously by taking the scaling factor less than 1. Means when we take scaling factor greater than 1, that makes the loss of samples permanently. Means number of samples present in the resulting signal is generally less than the number of samples present in the original signal. Okay, guys, if we talk about the scaling factor that we have done by less than 1, so of course in that condition, resulting signal will have the more number of samples than the original one. This is called the interpolation of discrete time signal. Understood? So the less number of samples available as in the resulting signal as compared to original, that's called decimation of discrete time signal. Okay, if the number of samples are more than the original signal, then we say it is interpolation of discrete time signal. Let's talk about another operation that's called time reversal. Then we will sum up the today's session. Let's write here third one, time reversal. Guys, if we talk about the time reversal operation, Suppose I have taken this signal f of n -2, -1, 3, -1, 2. As I have already discussed time reversal operation while analyzing the continuous time signal, the same philosophy guys available here, okay, applicable here simply. What we will do, we will simply make this n by -n. Okay, so I don't think I have to explain it so much. Simply I'll write here 3 because at n is equal to 0 sample will not be get affected at all, but sample present at 1, 2 will be simply get flip about the value axis, means the sample which is present at 1 will reaches at -1, which is present at 2 will reaches at -2, present at -1 will reaches at -1, present at -2 will reaches at +2. This is f of -n simply. I don't have the need to explain it so much because I have already explained it under the continuous scale. What we will say, rotation of signal about the value axis, okay, or we say rotation of the signal about value axis by 180 degree. We also say taking the mirror image of the signal. So whatever the values of n we defines positive, here we have defined the negative. So when we rotate it by 180 degree, so of course you can say the positive values of n becomes negative values of n, means -2, -1, 2 will be present here for the negative values of n, and here it is -1, -2 will be present for the positive values of n. Simple. Okay. So guys, that will be enough for the today's session. I think we will meet in the next class where we will talk about how we perform time shifting and time scaling, time shifting and time reversal operation combinedly in the discrete scale. That's a brief observation because we have done this observation in the continuous scale. So I'll just sum up, and I'm just saying to you, you should come with revising the continuous time scale where we have performed the combination of operation time shifting, time scaling simultaneously, time shifting, time reversal simultaneously, and all three of the operation time shifting, time scaling, time reversal simultaneously. What are their rules? What are their precautions? You should come with the revision. In the next class, I'll discuss that, and I'll also talk about some standard signals operation on the discrete time scale. Okay, so we will meet in the next class and we will make further discussion in the discrete time signal. So that will be enough for the today's session. Thank you.